Hello, my dear students. Today in this class, we will discuss transpose of a matrix, skew-symmetric matrix and symmetric matrix. So, let's start. Transpose of a matrix. Let A be a matrix of order m by n, then the transpose of A is denoted by A to the power t or A dash is an n by n matrix such that this for all I equal to 1, 2, m and j equal to 1, 2, dot n. Thus, A to the power t is obtained from A by changing its rows into columns and columns into rows. For example, if A equal to any matrix 1, 2, 3, 4, 5, 6 is 2 by 3 order matrix, then A dash or A to the power t transpose matrix of A is equal to, we know that A to the power t is obtained from A by changing its rows into columns and columns into rows. Therefore, we change the first row into first column. This is first row. We change into first column 1, 2, 3. Next, we change the second row into second column 4, 5, 6. This is 3 by 2 order matrix. A dash or transpose matrix of A equal to this. Next, we discussed properties of transpose. Properties of transposed of the matrices. Transpose of the matrices of the matrices. If for any matrices A and B, A and B of suitable orders of A and B of suitable orders, then number 1, transpose matrix of A whole transposed, that is A dash whole dash equal to A. Next, number 2, K into A whole dash equal to K into A dash, where K is a constant, where K is any constant. Number 3, A plus B whole dash equal to A dash B dash. Number 4, A into B whole dash transpose matrix of AB equal to transpose matrix of B into transpose matrix of A. These properties are very important. Remember, for any matrices A and B of suitable orders, then A dash whole dash, that means transpose matrix of A whole transpose equal to A. For example, let A equal to any matrix, we take any matrix 1, 2, 3, 4, and it is equal to, we know that changing the rows with columns, then we have the first row interchange to first column and second row interchange to second column. Therefore, it is equal to 1, 3, 2, 4, and it is whole list equal to the first row interchange to first column 1, 3, the second row interchange to second column, which is equal to A. Therefore, A dash all dash equal to A. Next, Ka whole dash equal to K into A dash, where K is any constant. Next, AB whole dash equal to A dash plus B dash. Next, A into B whole dash equal to B dash into A dash. Now, we discussed symmetric matrix. Symmetric matrix. What is symmetric matrix? If A is a square matrix and A dash equal to A, if A is a square matrix, A is a square matrix, A is a square matrix. Square matrix means the total number of rows equal to total number of columns, that is M equal to N. If A is a square matrix and A dash equal to A, then A is called symmetric matrix. What is symmetric matrix? If A is a square matrix, remember A is a square matrix and transpose matrix of A equal to A dash equal to A, then A is called symmetric matrix. For example, A equal to 2, 1, 5, 1, 0, minus 3, 1, 0, minus 3, and 5 minus 3 is 6, 5 minus 3, 6. Example, A equal to 2, 1, 5, 1, 0, minus 3, 5 minus 3, 6 is called symmetric because it is, this is a square matrix and A dash equal to, we know that transpose matrix of A is obtained by interchanging rows into columns and columns into rows. Therefore, the first row, the interchange the first row into first columns 2, 1, 5, and the second row interchange into second column, and we have 1, 0, minus 3, and third column interchange into third column, and we have 5 minus 3, 6, which is equal to A, 2, 2, here 1, here 1, 5, 5, 1, 1, 0, 0, 5 minus, which is equal to A. Therefore, A is called a symmetric matrix because A is a square matrix and A dash equal to A. A is a square matrix and A dash equal to A. Therefore, A is called symmetric matrix. Now, we discuss skew-symmetric matrix. Skew-symmetric matrix. Skew. What is skew-symmetric matrix? If A is a square matrix and A is equal to minus A, then A is called skew-symmetric matrix. If A is a square matrix and A is equal to minus A, then A is called skew-symmetric matrix. For example, A equal to 0, 2, minus 3, 0, 2, minus 3, minus 2, 0, 5, minus 2, 0, 5, and 3, minus 5, 0. We take an example. A equal to 0, 2, minus 3, minus 2, 0, 5, and third row columns are 3, minus 5, 0. A is called skew-symmetric matrix because A dash equal to, we know that transpose of A or A dash, we interchanging the rows into column and columns into row. Therefore, we have 0, 2, minus 3, minus 2, 0, 5, 3, minus 5, 0 equal to, taking common minus from this matrix, then we have 0, 2, minus 3, minus 2, 0, 5, 3, minus 5, 0. 0, 2, minus 3, minus 2, 0, 5, 3, minus 5, 0, which is equal to minus A. Here, A is equal to minus A. Therefore, A is called skew-symmetric matrix. What is skew-symmetric? If A is a square matrix and A is equal to minus A, then A is called skew-symmetric matrix. For example, A is skew-symmetric matrix because A is equal to minus A. Also, A is a square matrix. Next, we discussed theorem, two theorem. Theorem number 1. For any square matrix A, square matrix A with real number elements, with real number elements or entities, elements, then A plus A dash is a symmetric matrix, and A minus A dash is a skew-symmetric matrix. Skew-symmetric matrix. Theorem 1. For any square matrix A with real number elements, then A plus A dash means transpose of A plus A dash is symmetric matrix and A minus A dash is square symmetric matrix. Proof. Let B equal to A plus A dash. Then B dash equal to A plus A dash whole dash. Let B equal to A plus A dash, then transpose matrix of B is equal to A plus A dash whole dash. From properties, we can write from the properties A plus B whole dash equal to A dash plus B dash. Then this can be written as A dash plus A dash whole dash equal to A dash plus A dash whole dash. We know that A dash whole dash equal to A, and A is equal to A plus A dash. Therefore, A plus is equal to B. Since B dash equal to B, or A plus A dash equal to A plus A dash. Therefore, B is a symmetric matrix. If A is a square matrix with real numbers elements, then A plus A dash is a symmetric matrix. Hence proof. Next, A minus A dash. Next, let B equal to C equal to A minus A dash. Then C dash equal to A minus A dash whole dash. This equal to A dash minus A dash whole dash. We know that since A minus B whole dash equal to A dash minus B dash. Therefore, this can be written as A dash minus A dash whole dash. Therefore, A dash minus, since A dash whole dash equal to A, therefore, this is equal to A minus A dash equal to minus C. Since C dash equal to minus C, or C, A minus A dash equal to minus A minus A dash. Since C dash equal to minus C, therefore C is a skew-symmetric matrix. If A is a square matrix with real number elements, then A minus A dash is a skew-symmetric matrix, because A minus A dash equal to minus A minus A dash. Next, theorem number 2. Theorem 2. In a square matrix, theorem 2. In a square matrix, can be expressed as the sum of a symmetric and a skew-symmetric matrix. Skew-symmetric matrix. Any square matrix can be expressed as the sum of a symmetric and a skew-symmetric matrix. If A is a square matrix, then it is expressed as a equal to 1 by 2 into a plus a dash plus 1 by 2 into a minus a dash. If A is a square matrix, then it is expressed as sum of a symmetric and skew-symmetric matrix, that is A equal to 1 by 2 into a plus a dash plus 1 by 2 into a minus a dash. Because since A is a square matrix, then a plus a dash is also a square matrix, and 1 by 2 into a plus a dash also square matrix. If A is a square matrix, then a minus a dash is skew-symmetric matrix, then 1 by 2 into a minus a dash also skew-symmetric matrix. Now we will discuss exercise 3.3, question number 1. Find the transpose of these matrices. Solve. Question number 1, Roman number 1. 5 1 by 2 minus 1. Transpose of this matrix is obtained. We know that interchange its rows with columns. Then we have, after transpose, we have 5 1 by 2 minus 1. This is order 3 by 1. This is order 1 by 3. Next, question number 2. 1 minus 1 2 3. Transpose equal to interchange the first row into first column. Then we have 1 minus 1 second row into second column 2 3. Next, number 3. 1 5 6 root 3 5 6 2 3 minus 1. Transpose equal to the interchange the first row into first column. Then we have 1 5 6. Next, interchange the second row with second column. Then we have root 3 5 6. Interchange the third row with third column. Then we have 2 3 minus 1. The result is this. Next, we discuss question number 2. Question number 2. If A equal to minus 1 2 3 5 7 9 minus 2 1 1, and B equal to minus 4 1 minus 5 1 2 0 1 3 1. Then verify that question number 1, A plus B whole dash equal to A dash plus B dash. If A equal to this and B equal to this, then verify A plus B whole dash equal to A dash plus B dash. Solution. A equal to minus 1 2 3 5 7 9 minus 2 1 1. Then A dash equal to, then it is equal to, we have the first row interchange with first column minus 1 2 3. The second row interchange with second column. Then we have 5 7 9. the third row interchange with third column, then we have -2 1 1. Next, b equal to -4 1 -5 1 2 0 1 3 1. Then b dash equal to, we know that the first row interchange with first column, then we have -4 1 -5 and so on 1 2 0 1 3 1. Left hand side, a plus b whole dash equal to a equal to -1 2 3 5 7 9 -2 1 1 plus b equal to -4 1 -5 1 2 0 1 3 1 all list is equal to -1 -4 -5 2 2 plus 1 3 3 -5 -2 5 plus 1 6 7 plus 2 9 9 plus 0 9 -2 plus 1 -1 1 plus 3 4 1 plus 1 2 all this is equal to the first row interchange with first column, then -3 2 -2 6 9 9 -1 4 2 -1 4 2. Left hand side is equal to -5 6 -1 3 9 4 -2 9 2. Next, right hand side equal to a dash plus b dash. A dash equal to this -1 5 -2 2 7 1 3 9 1 plus b dash equal to -4 1 1 1 2 3 -5 0 1. This equal to -1 -1 -5 5 plus 1 6 -2 plus 1 -1 2 plus 1 3 7 plus 2 9 1 plus 3 4 3 -5 -2 9 plus 0 9 1 plus 1 2 -5 6 -1 3 9 4 -2 9 2. Therefore a plus b all this equal to a dash plus b dash, or left hand side equal to right hand side, hence proof.